Here's a fun toy. You've probably seen one of these somewhere before. They were a pretty big deal up until we invented gunpowder. This one's made of kinetics and rubber bands, and it can throw this washer at about 50 meters per second. Works better if you actually put the washer on first. Probably take someone's eye out if you weren't careful. Makes you wonder though, doesn't it? If you can do this with building blocks and office supplies, what can you do with titanium and carbon fiber? Why have we never seen a supersonic trebuchet? I asked myself this question last fall, and I was expecting to get a decent-sized design project out of it, a few months, something you can really sink your teeth into. I was very disappointed. Turns out building a supersonic trebuchet is pretty easy. Here's how I did it.
What we're looking at here is a design optimization problem. You have a constraint, throw above 350 meters per second, and a cost function, difficulty of construction and design. Ideally, we need a way to search the portion of the design space that satisfies the constraint for regions that minimize the cost function. In toy problems, this can be approached very directly, but in a more complex real-world problem like this, we need to find some tricks.
First, regardless of what else we do, we need a model. The cost function will return some value based on performance of the machine and how it's made, so we need a relation between the two. My model solves the dynamics of a frictionless double pendulum, where the first link is driven by a torque that is a function only of angle. This is different from a real trebuchet in some important ways, which we need to keep in mind for later, but it's a good starting point. The constraint is a bit tricky. Since it's a constraint on the outputs rather than the inputs, and the map from design parameters to performance is quite complicated, we can't approach this one directly. We can do well enough with energy conservation though. After we get a look at typical efficiencies of these machines, we can choose projectile mass needed to achieve the desired speed based on the available energy, which is in turn determined by how we build the puller. The constraint will only be approximately satisfied, but in this case it's good enough.
The cost function is trickier still. How do we formalize the notion of difficulty of design and construction? Surprisingly, this is a problem with a straightforward answer. We can derive an equation that quantitatively compares the difficulty of different designs. To start, let's choose some reasonable-looking values of the design parameters based on other working machines we've seen. Now, let's optimize over the least obvious one, arm rotational inertia, to get the maximum speed. We see that there's a local optimum. Further testing shows that varying the projectile mass causes linear variation in optimal inertia. We can also learn that the maximum sling tension doesn't change much with projectile mass as long as the inertia of the arm is varied to match. So as we throw lighter projectiles, we need equally strong arms with progressively less inertia, all else being equal.
Thus solving the problem once and for all.
But
Once and for all!
This suggests that arm design gets harder as speed increases, which agrees with our intuition. If we take our reasonable-looking machine and try to make it throw at Mach 1, we will likely find that the inertia and strength requirements of the arm are difficult or impossible to satisfy. We can always make the frame stronger or add more rubber, but the arm alone requires finesse. We can thus safely base our cost function entirely on the arm requirements. The question is now a bit narrower. How do we compare the difficulties of different arm specifications? Failure of an arm comes either from yielding or lateral torsional buckling. So stiffness and yield strength are important. Physical dimensions of the arm come from length, rotational inertia, and density. We can then use the Buckingham-Pi theorem to find the relation between maximum force and all these properties. We end up with this. A quick numerical experiment using FEA shows that the unknown function can be approximated as a power law. and the full expression looks like this. We can break it into a term that represents the goodness of a material for arm design, and a term that expresses the hardness of the design problem. Harder designs require better materials to solve with a given geometry. This has the nice side effect of telling us which materials are best, which is not a trivial question. With the difficulty function in hand, we can try to eliminate more free parameters by checking if any should simply be maximized or minimized. What about the length of the arm? Remember how we found earlier that the optimal inertia scales with projectile mass? If we put this together with the fact that inertia scales with the fifth power of the length scale, we see that arm inertia scales with the length squared. Force on the sling scales with 1 over L, as this is just proportional to the acceleration along a curved path where we scale the curvature. Plug these scaling relations into the design hardness relation, and we find that hardness scales with arm length to the power of 1.8, all else being equal. Therefore, we should simply make the arm as short as possible. This ends up being practically limited by the fact that puller speed shouldn't be too high and the inherent limitations of joining and terminating rubber. It turns out we can also do away with angular stroke. Let's supply a fixed amount of energy, constrain the final arm angle and launch angle, and optimize over sling length, arm inertia, and finger angle to find the maximum speed. We see that throw speed is practically invariant with angular stroke, while arm design hardness is strictly decreasing. As such, we just make the angular stroke as large as practical. After doing some experiments to estimate the effective air resistance, I settled on 6 radians, just under a full rotation.
The effect of varying the initial angle between the arm and the sling is less clear-cut. As it increases, arm design hardness decreases, but the length of the sling increases, making the platform that holds the projectile harder to build as well as increasing drag losses. It would be interesting to see this addressed by modifying the arm design hardness function and incorporating drag into the model, but we do run the risk of spending the rest of our lives modeling and never actually building anything. 0.26 radians seemed like a good balance, and I just went with that.
At this point, I'm going to introduce a few more constraints on the problem. Budget, size, and model limitations. I built this machine on a very low budget, about $30 for the first version, and later another $100 for a new arm. Most of the parts were spares lying around my shop. The frame and axle limited puller force to 6 kilonewtons. The size of my car and the metal I had on the shelf limited the puller extended length to 1 meter. The puller speed was kept under 10 meters per second, both for efficiency and reasons of model accuracy. This particular set of constraints created an interesting coincidence. The minimum achievable arm design hardness is almost invariant with arm length. However, shorter arms have lower drag losses and lower material costs, so I went with the shortest I thought I could get away with, 0.4 meter. In hindsight, I probably could have gone as low as 0.3 meter. Similarly, I chose 3/8 inch steel balls as the best match for the available energy, but the efficiency ended up being higher than expected, and 1/2 inch may have been workable as well. With all these parameters fixed, we can find the relationship between inertia and design load of the arm. This gets plugged into our FEA study to find a suitable arm geometry. In this case, we find it's difficult to get the inertia low enough for optimal performance, but we can still reach predicted speeds in excess of 450 meters per second. Locking in the arm geometry sets arm mass, center of mass location, and arm inertia. It also severely limits the options for sling length. Given the time to iterate the arm design, I settled for a slightly suboptimal configuration with a predicted throw speed of 466 meters per second. And that's it. The optimization study is finished. It's off to the shop with me, but you get to skip straight to the fun part. This is the result of that study. It's a bit of a strange-looking beast, but conceptually identical to the toy model I showed you earlier. It has a frame, a rubber puller, and a throwing arm. The rubber pulls on the rope, which is wrapped around this pulley, making the arm spin. The ball starts off sitting on this little platform, where initially it's held in place by the rotational acceleration force. As the rotational speed increases, the centrifugal force rises and overwhelms the tangential force holding the ball in place, causing it to lift off the platform and beginning the harvesting motion. During the harvesting motion, the angle between the arm and the sling increases, until the free end of the sling slips off the finger, and the projectile flies away. Now that you know how it works, let's see it move.
And here we go. It's already pretty quick to the human eye, but it's a long way from Mach 1. To get there, we're going to need more rubber. A lot more rubber. This should do the trick. We're also going to need someplace a little bit less populated.
Ah, that's better. First, let's see a low-speed shot at about 200 meters per second. In 3, 2, 1. Alright, we've reset the trigger. Now let's load a new ball. Okay, it's ready to go. Let's crank this thing all the way up and see if we can make some noise. One of the things I love about working with wood is all the menacing creaking noises it makes when you load it. It really makes you appreciate how precious and fleeting life is. Alright, 3 inches to go. 5 turns. 1, 2, 3, 4, and 5. Whew. Alright, this is it. This is what you came for. The fastest trebuchet in the world. In 3, 2, 1. Never gets old. That's a purely mechanical device, throwing at over 400 meters per second, powered by rubber bands.
The high-speed shots aren't exactly beautiful, but they are useful for evaluating performance. This is played back at 1/66th of real speed, and the throwing motion is clearly visible. By scaling from the length of the arm, we can calculate the launch speed, which in this case is 490 meters per second. If anyone with a fancy camera wants to try getting a better video of this, I would be very keen. The sound on that last shot was a bit of a dull thump and muted echo, but it varies dramatically by location. If you're standing in an unlucky spot, it can make your ears ring. Here's 2 other shots for comparison, both done with the old plywood arm.
Alright, firing in 3, 2, 1. Oh man! And this is what it sounds like at full power. In 3, 2, 1. This machine is one of my favorite illustrations of the power of engineering. It's small, easy to understand, and costs next to nothing. But seeing it throw is spectacular, and you could never arrive at it by accident. The design and build process only took about 3 weeks start to finish. Now, making the video, on the other hand, but it was well worth it. I went into this project expecting a difficult, expensive one-off. What I found was much more interesting. Anybody with a workshop and some basic tools could build one of these. I've included links to the detailed drawings and simulation code in the description. feel free to get in touch by commenting on the video or the GrabCAD or GitHub pages. I think the supersonic trebuchet is a machine whose time has come. Anyone out there looking for a project?